The immense gravity of a black hole is capable of stretching and shredding a star into a swirling vortex of subatomic particles. If you were to fall in, the transition would be imperceptible at first. It is like swimming in a river that leads to an enormous waterfall. The current simply speeds up as you drift along. Eventually, you cross a threshold called the event horizon. Beyond this point, the current moves faster than light, making it impossible to swim back to safety. This boundary creates a permanent cosmic quarantine. Anything that falls inside is forever cut off from the rest of the observable universe. In physics, information refers to how particles are arranged. These carbon atoms form coal, but when rearranged into this specific lattice, they become a diamond. The atoms are the same. The information is what makes them different. Quantum mechanics dictates that this information can never be lost. If you burn a diamond, it turns into ash and heat. But if you could track every atom and every wave of radiation, you could, in theory, reconstruct the original diamond. But black holes present a problem. They slowly leak mass through Hawking radiation over trillions of years until the black hole eventually evaporates, leaving nothing behind. If the black hole disappears completely, all the arrangement data that fell into it appears to be deleted from the universe. This is the information paradox. If black holes can truly delete information, the foundation of modern physics is broken, meaning our current mathematical models of reality are incorrect. To resolve this contradiction, physicists have tested several different hypotheses. One option is to accept that information is simply lost. This requires us to abandon our current laws of physics and start over with a new set of rules. Since we have no idea what those new rules would be, most scientists are reluctant to take such a drastic step. A second option suggests the information is hidden. Perhaps it branches off into a separate baby universe or remains inside a microscopic remnant left behind by the black hole. However, sequestering data in an unreachable location is effectively the same as losing it. To keep the math of our universe consistent, we need a way for that information to remain accessible. A third possibility is that the information never actually leaves our reach. We may simply be looking at how black holes store data the wrong way. Every region of space has a limit on how much information it can hold. Think of it like a room that is packed so tightly with laundry that not even a single extra sock can fit inside. When you try to force more information into a black hole, it cannot fit inside the volume. Instead, the surface area of the black hole expands by one tiny pixel for every bit of data you add. On a microscopic level, three-dimensional objects flatten into two-dimensional codes that are painted directly onto the event horizon. As the black hole evaporates, the escaping Hawking radiation can interact with these surface pixels and carry that information back out into the universe. This solves the paradox by making black holes the most compact storage drives in existence, preserving everything they consume on their surface. This solution indicates that three-dimensional objects can be perfectly described by data on a flat two-dimensional surface. This is the core principle of a hologram, a flat piece of plastic that encodes a full 3D image. An astronaut falling into a black hole would still feel like they are living in 3 dimensions, but from the perspective of an outside observer, that person is actually a set of flattened data points on the event horizon. In this model, depth and volume are a matter of perspective rather than absolute physical facts. Black holes are simply matter in an extreme state, but they follow the same laws as the rest of the universe. If the math of the holographic principle applies to them, it should theoretically apply to any region of space, including our own. If you push far enough into the star field, the perspective snaps. These stars are actually flat, glowing pixels on a two-dimensional screen. It is mathematically possible that our entire three-dimensional world is a projection of data stored on a flat boundary at the edge of the universe. By investigating the death of stars, we found a mathematical path to a universe where 3 dimensions emerge from 2.